Okay.
So I'm ready when you guys are?
I'm ready. Get out my magic red pen. Start bleeding.
All right. So my name is Wagner Wieson, and today we're going to be going over DigiMesh reliability in high-speed vehicular applications. This is the agenda for today. Basically pretty much boilerplate stuff, the introduction, the motivation, my research question, the related works that I found, what methodologies I've used, my assumptions, my results and conclusions. So, why is this important? Well, in the recent study, more or less of basically facts, statistics, in 2015 there was about 12,000 deaths due to EMS response times, and 275 of these people actually died after waiting about more than 30 minutes and up to even 2 hours. So why is this important? Well, communication is very important, especially as technology advances and as cars become smarter. For example, even the vehicles that aren't smart, the older vehicles. Let's say, for example, you're driving an older vehicle, and a lot of them have OnStar and these safety mechanisms after they get into crashes, but some don't. So what about those people that can't send out any distress messages if you're crashed somewhere and you're unconscious and you're by yourself just in the middle of the night? So here's where kind of the applications and protocols that I've kind of looked into. First candidate was Bluetooth. It's low powered, it's pretty common, but the only problem is that it's not very fast, it's not performance oriented. As maybe some of you know, when you use like a Bluetooth speaker or a Bluetooth mouse, you probably go away about 10, 20 feet, and you already start hearing the music cut out. So Bluetooth's not very reliable. Zigbee was actually my next candidate. The only problem with Zigbee is that it can't organically grow, and it needs a coordinator. By this network diagram, it basically means that there needs to be a centralized brain that coordinates what the network is. So you can't actually start a network just organically by having two nodes just be there. The next technologies, which we'll briefly discuss a little bit later, is DSRC and 5G. These technologies actually seem pretty good as an uplink method. Unfortunately, a lot of their drawbacks include like infrastructure costs, and the problem with them is that, for example, 5G is probably promised to be in 2020, but it's not really a technology that is concrete yet. It's kind of a lot of speculation. And then lastly, I kind of looked at DigiMesh, and that was my protocol that I decided was, well, this looks promising. It's low powered, it can create local area communication, and it organically connects, as I'll explain later. So the motivation for this was actually first the affordability. When I first started my research process, I looked into DSRC heavily and tried to price out some radios that I could use for my experiments, and these ran up into the thousands of dollars. So it's not really very efficient for the home gamer, let's say, to get into it. The next thing is open source. While DigiMesh is kind of a proprietary protocol because it's made by Digi International, it doesn't have any restrictions on what you can program. So there's open source libraries basically that you can program. Anybody can go and download and use their Java API. The other part I thought about is it's agnostic. So it doesn't matter what you have, what vehicle, what model. A lot of these DSRC radios, if they were to be put in production, they're kind of baked into the vehicle itself, and each manufacturer might have something. You don't need to have any specific brand. And then signal channel is something that I want to touch on because realistically, DigiMesh can't really do it alone. And I don't think that DSRC or 5G can do it alone either. The idea is having the second independent system as a backup is kind of the motivation for the research, and that you actually bake in security there, just because you're not integrating the system with like the vehicle's electronics. For example, in the news there was the Jeep that was compromised just because they had the LTE connection with like the infotainment system. So I want to answer this research question: how reliable can this low-power DigiMesh device transmit signals at highway speeds? First, I just want to talk about what DSRC kind of is a little bit, and then what it's currently used for. DSRC stands for Dedicated Short Range Communication. It's actually kind of an old protocol. It was allocated in 1998 by the FCC. It was actually based on the 802.11a standard, the wireless standard. Its main goal was to prevent and inform of accidents. For example, if someone broke extremely hard around the corner where you can't see them, it's a blind corner, you'd be able to get notified, hey, someone's braking extremely hard in the corner, be alerted, slow down before you get to that blind corner. And V2V stands for the communication can actually, one car can talk to another car, vehicle to vehicle, and then vehicle to infrastructure, you can actually use infrastructure to be able to talk out kind of like the gateway. Next, I have DigiMesh. So this is the protocol that I'm studying. It was actually created in 2012 by Digi International, and it's based on the 802.15.4 standard, like the wireless personal network. It's purely infrastructureless, so you don't need to have anything set up. As long as they're on the same channel and on the same network ID, they can start communicating immediately. All nodes are considered routers, so again, you don't need to have a coordinator specifically. And there is 128 AES encryption, which for security standpoint is pretty secure for an IoT, like low-powered device. This was used in a research paper where some researchers tried to use this on cars, kind of platooning. So like they would just kind of communicate to each other and try to stay in a single file line. But the maximum reach speed was 7 miles an hour. And for my research, I wanted to see what highway speeds would be. So this kind of brings me to an overview of what my testing is going to consist of. Basically, I kind of have this kind of configuration where I have the primary vehicle and then the stationary vehicle. And realistically, the challenge was how do I isolate relative velocity as the independent variable? And in order to do this, I had to put a boundary or make a distinction between effective and communication range. For example, communication range would be something that the radio might pick up a packet from a really long distance, but it can't keep receiving packets. It might just get a reflection or something. Whereas the effective range would be you have a 99% reliability that you're going to get this packet in this area. And that's where I established the baseline using the entry coordinate and the exit coordinate for my test, which I'll explain a little bit in further detail. So my assumptions, just kind of, I think the basic stuff, just my GPS that I used was accurate. I used an airfield, which kind of represented a highway. All my devices were working, altitude change didn't really matter, and environmental factors such as like sunny, windy, snow, rain wasn't really gonna make any difference. My limitations, I kept my transmit and receive fixed on my radios. My granularity was actually 50 hertz, which is really good actually for a commercially available radio. It means that it samples 50 times every second. And performance depended on the vehicle, and radio interference was limited by the vehicle chassis because the device was inside of the vehicle, basically like a Faraday cage. My delimitations, basically energy consumption, I'm not going to really look at that. I'm only going to focus on DigiMesh. I'm only going to test 2 nodes and in the 2.4 gigahertz spectrum, and then I'm only going to have 1 moving vehicle at a time. My hypothesis, the moment is, what I'm going to be looking at is the packet delivery ratio, and my null is that it will not change due to relative velocity, and my alpha was that it will actually decrease due to relative velocity. And packet delivery ratio, which I name PDR, will be the variable I'm testing. Here's the equipment that I used, and basically the 2 vehicles I had. I had one of my ex-boss actually let me use his car. Had to use the spectrum analyzer. I had the XB-S2C model, Raspberry Pi 3, the GPS, and a couple of MacBooks to kind of interface all the stuff. The environment, this area was actually pretty clear. I ran the spectrum analyzer for a few minutes and had basically a solid noise floor. There's no spikes indicating that there's any other devices in that field, in that range. And this was actually in Riley Airfield in Attica, Indiana. It's not in the best shape, but it actually worked out pretty well. So the field work, how exactly did I conduct this experiment? Basically, I had to record the entry and exit coordinates for my boundary. And in order to do that, I had to make sure that I had a static PDR ratio of 99%. So the idea being that within this zone, I'm expected to get 99% packet delivery ratio without the vehicle moving. And I did this for both the entry and exit with the primary vehicle facing the stationary vehicle. This was to kind of rule out any errors of like the antenna propagation. Maybe it would be biased towards the front or the rear because the antenna had the most peak radiation gain at the front of the vehicle. Realistically, it didn't matter as long as I relatively kept the same on both sides. And I tracked my primary vehicle, which was moving past my stationary vehicle using the GPS I mentioned earlier. And before each test, I actually tested 11 categories from 10 to 60 miles an hour at 5 mile an hour increments. And before I tested a new speed category, I made sure all my devices were synchronized with a government NTP server. And this was done so that way I have my UTC time down to a millisecond accuracy in order to later use it as a common denominator for all my data, which I'll explain. My GPS, there's this thing called NVA Messages, and basically these are the messages that are produced by the GPS chip to give you either bearing or latitude, longitude, speed, etc. I used RMC, which is the recommended minimum sentence C, and this gave me latitude, longitude, the validity of my message, and the speed, which is really all I really needed. I actually measured the error of my GPS device. I went down to the airport and they had a GPS kind of plaque on the ground. So that's like a known point down to the centimeter. And I just sat there and got about 280,000 samples. And I found out my GPS had about 1.6 meters of error. The manufacturer on their data sheet had around 2.5, so I thought this was actually pretty good. And back to the 50 hertz update rate, that's very important. That's the fastest I could get commercially, because if I was doing it with 1 hertz, then I would get a data point every second. And when you're traveling at 60 miles an hour, that's not going to be very granular. So here's kind of the methodology that I used for the GPS. What's really important to note is just that I actually input my stationary vehicle coordinates and my entry and exit coordinates, and that allowed me later to parse through them. The way that this code works is that I have a semaphore, which is like a flag, and this semaphore is used to determine once the test has begun and I start writing data, if my GPS signal becomes invalid, then I will restart the test. It'll tell me to stop, that way I don't have any bad data. And then I eventually also got the UTC time, and I wrote it all down in a log file to parse later. The DigiMesh device itself, the primary vehicle actually had attached this, on both vehicles I attached it in this same configuration. The primary vehicle its job was to basically receive packets and calculate the static PDR and then just log the whole time. The static PDR again is when the vehicle is not moving, what is the packet delivery ratio in order to set those boundaries, that 99% boundary. And I did this by traveling closer to the stationary vehicle, and when I reached 99%, I back up until I dropped, and then I kind of found the sweet spot in the middle. The stationary vehicle, it was just sending messages, just broadcasting messages at a 40 millisecond interval. I actually found out 40 milliseconds was the best interval because just in a controlled benchtop test, I was testing it with about 100,000 packets. I was testing to see what would be a good interval, because if it was too fast, then you'd actually miss a lot of packets and you'd get like 80 or even 60% PDR. And then I also didn't want it to be too slow because I wanted to make sure that I had a lot of packets throughout these tests for my statistics. So both of these jobs for these devices were just the log data the whole time. And that brings me into how I put all the data together to get my dynamic PDR for each velocity. The important part of this is I have to input my sender, receiver, and GPS data. And then from there, all I'm doing is basically finding the boundary at the time location down to the millisecond when I enter and when I exit. And then I cross-reference that with my sent and received packets and look at the time code for those as well. And then I only count the amount of packets. For them, it's just a simple math problem. I just count the packets that were sent and packets that were received inside the packet delivery boundary that was 99%. And then received packets divided by sent packets, and that gave me my PDR. So the results. I actually kind of have two separate things here. First, the transmission opportunity. This is sort of synonymous with the effective boundary. All it means is that this is the time and length that the total amount of packets can be sent. It's not even received. We're just looking at what's the possible amount of packets sent, and I was actually able to model that really well because it was a nice power curve. And next is the PDR versus velocity, which is basically what my hypothesis is, and finding the correlation between those. Here I actually noted down what the transmit opportunity was. So within this area between these two dots, statically I would have 99% packet delivery ratio, and this was about 103 meters of total time. And using this, I was able to basically jot down just what my average packets that were sent at different relative velocities. And this actually turned out to be a very nice power curve. I tested it using a log scale, and it was very linear. And then this best curve fit line actually worked out really well. And of course, it's going to stay consistent because you have a fixed length of time, and you have a fixed length of packets that you're sending. So you can easily model, depending on how fast you're going, how many packets can you send in that time frame. Next, I actually have the results for my packet delivery ratio. I used, there's my statistical hypothesis there. I used an alpha of 0.015. And this is just the packets that I got. I averaged the packets. I took about 110 samples, and I averaged all the packets for the sent and received and got my packet delivery ratio, as you can see here. Next, I saw that when I did a scatter plot for all my points, this was linear, which meant that I could actually do the Pearson correlation test. And as you can see, these are the averages with just the trend line for those. Here we actually have the Pearson correlation, and I did have linear results with an alpha of 0.015. My R value, which is the coefficient of correlation, was negative 0.66. And then I used that to find out my test statistic. And my critical value was derived from the 0.015 from a t-table using n-2 degrees of freedom. And I did actually find out that there's sufficient statistical evidence that at 0.05 level that there's a linear relation between the packet delivery ratio and relative velocity. And this was because my test statistic was lower than my critical value here. In conclusion, I kind of have two models for the transmit opportunity and the PDR. I believe the transmit opportunity one is going to be actually be able to predict how many packets I can send For the PDR values, I think that there still needs to be, like, it's effective, but I still think that there needs to be more testing at higher velocities. And just for grins and giggles, I kind of plugged a few values into the equations, and I used an 80% cutoff to figure out at what speed I would have to go to get an 80% packet delivery ratio. I got around 210 miles an hour of relative velocity, and then I calculated how many packets I can send within that 210 mile an hour velocity window, which gave me about 17 packets and 1.24 kilobytes of data, which using that amount of data, I believe can still be used to send out distress messages. So, because each for example, like coordinates or time of day, location, stuff like that, this 1.2 kilobytes will be more than enough. Plus, at 215 miles an hour, that's like a worst case scenario. So these are kind of my appendix. This is kind of the equations that I got from using my best fit curve. And my DigiMesh radiation pattern, it was using the PCB antenna, and I actually talked to the manufacturer to get these. It's not perfectly omnidirectional, but I think it was worked out pretty well for my experiments. And the references for today's presentation, and that'll be all. If there's any questions.
Let me jump in, Bogey.
Sure.
Go back again to the very beginning there.
Very beginning.
And I'm sorry I missed because I was looking a few things up. I'd like to just want to make sure we're on the same page, and if you're going to publish this, that we're using the same terms here. Next one. Next one, I believe you on that one. Bluetooth slow.
Slow.
Are you sure you don't mean range issues? I mean,
No, so actually, for it to get
Bluetooth low power is fairly slow, but Bluetooth itself is not.
So what I was talking about is the actual connection time required.
Gotcha.
So
okay.
like, yeah, as vehicles are passing by.
Is that clear in your paper that we're talking
Yes.
about the
Yes,
actual
yes, yes.
connection time, not throughput slow?
Yes,
Okay.
yes. On the throughput, I wasn't much of a concern. It was just
And that's what I figured.
Right.
Yeah, you don't care about throughput.
Right.
Let's get connected and send
Yeah.
little bits of data. Okay, so is DigiMesh based on ZigBee or XBee?
So XP is just the physical platform that they can both work on,
Mhm.
but DigiMesh is based on 802.15.4. So it's part of that network. It's very similar to ZigBee.
Mhm.
It uses the same channels, it uses the same channel widths, all that. The only difference is that it doesn't need this hierarchical infrastructure to get it to work.
So same radio, same modulation, simply
Correct.
the upper layers, how they handle traffic are set
Correct.
up differently.
Correct.
Okay. There was another slide or two.
Okay.
You said something about single channel, and I'm
Oh,
not
yeah,
sure
this
that's
one.
what you really mean.
So
Single
single-
source or single?
So, right, because signal channel is a little bit ambiguous. The idea being is like having, for example, multiple channels in which you can get data out. For example,
Okay.
right, if you had a vehicle equipped with both an uplink technology like DSRC or 5G, you can have the secondary device on there which is fully independent of either of them. And the idea being someone that doesn't have that ability to have that uplink connectivity, they could just have this local area connectivity, and they can still transmit signals to passerby vehicles that have those uplink technologies, which could then alert EMS services.
Okay. So how would we clarify that rather than me in the radio world thinking single channel meant 20 megahertz
Oh,
of bandwidth?
no,
at a
right.
certain- Are you sure your term's correct there?
So I think it maybe multiple architecture might be a little bit better
Okay,
word.
just a thought.
Okay.
I've got that highlighted. We
Right.
need to talk about that because when I saw that, I was like, no, it's not.
Right.
Also, a couple more. I just
Sure.
got another couple technical questions for you. Keep going where you talked about your signal to noise ratio.
Oh, like here.
Yeah, noise floor of negative 75 dBm out in the middle of nowhere. You sure?
Well-
You're reading I would expect a negative 100, negative 105.
So I'm reading the top. I was reading the top of this this value here.
Okay, is it a calibrated scope?
That
Because
is
that's
something-
way, way, way high, Bogey. That's like airport, in the middle of an airport
Right.
high. I mean, a terminal kind of
Right.
noise that you would see.
It did seem. I did think that it seemed kind of high, but I was just kind of like, okay,
Is
the
that
scope
our spec
yeah, it's
analyzer?
our spec analyzer. I figured like, oh yeah, it's fine.
Yeah, well, then it needs calibration. I'm also wondering, and that's at 2.4, or in your given frequency.
Yeah,
is
that,
it
I
showing
zoomed
that?
in about 40, 30 megahertz wide, and then I was on basically 2.410 as my
Okay,
center
we need
frequency.
to, okay, we just need to clarify that, because again, I'd like to see this published, and somebody like me is gonna look at that and go, where the
Right.
hell were they with a negative
Right.
75 noise? You know, that'll wipe out Wi-Fi right there. That's crazy, so.
You can still see. Well, obviously, yeah. You can still see the. I did have a 5 dBi gain antenna on it. I don't think that should have really caused that much for the noise floor.
Usually what I have to do is I have to stretch that way out so that I've got literally a bandwidth of maybe of 101K, and
Okay.
you'll see it shrink on down. Again, we can talk offline. Let's just
Sure.
make sure you get that right in the paper for a final edit, because that's not correct. So,
Okay.
but other than that, looks great.
I just have a question because you listed this antenna thing. It doesn't look like very uniformly distributed. So you might want to mention how you lay out your antenna during the testing.
Yeah, could you
Right.
go back to, I'm sorry, I was looking something up real quick when you got to that.
So I mentioned in the paper as well, and I had the highest gain pointed out towards the window.
Okay.
And then the idea being that as long as I kept everything relative,
Mhm.
then the values didn't necessarily have to be perfect.
Okay.
Which is why I guess I could be able to get away with not having a perfectly uniform antenna.
Yeah.
Plus the chassis of the vehicle, and I even noticed here this was pointed northeast,
Mhm.
so I actually was able to get a little bit farther distance than I was here at the entry towards the rear of the vehicle. But I kept both of these points the same, and then when I did my test, I actually ran both directions in order to kind of minimize the impact that an uneven radiation pattern could potentially cause problems.
You know, this makes sense to me, actually, off of a board
Yeah, it's PCB.
level. Yeah. It's not pretty, but it
Right.
makes sense.
It was funny because I just looked at, before I contacted them, I looked at what the documentations that they had, and then they said that the PCB antenna was within 0.6 dBs of their omnidirectional or like chip antenna, and I wanted to actually contact them and like, can you give me like the full azimuth and the elevation?
Is that where this came from?
Yeah.
From them? Okay.
Yeah,
So they've put it in a chamber and seen this, but obviously it worked okay, even though that's one
Yep.
ugly ass radiation pattern.
Because I was thinking XZ, YZ probably doesn't matter that much. It's really the XY really matters, right?
Mm-hmm. Well, because I also included the image of like which way it's looking. So like that's like the top-down view, and it was both in both
Oh.
directions top-down,
Okay.
and then the forward and the side kind of looked a little iffy.
Yeah.